This is quite a nice little trick to do an implicit differentiation. So we're going to set up our function to equal 0. So if it's not equal to 0, we have to rearrange it to equal 0. And then we're just going to call our function equal to z. So we know that z is equal to 0, so any change of z is going to be 0. Z is always 0, doesn't matter what's going on, the change of z is going to equal 0. So that's a useful thing we're going to use. And then we're just going to use our standard chain rule, noting that dx is 1, so that disappears over there. Okay, so we're going to use these two tricks to sort this out. So here's an example. So the first thing we want to do is we want to rearrange that to make it equal to 0. So xy plus sine y minus 2 equals 0. I've got the whole thing equals 0. And now we're going to let z equal this thing, xy plus sine y minus 2. And we know that equals 0, so we know that the z equals 0. So we're going to try and figure out the derivative of z with respect to x, which we know is partial z partial x times dx, which is just equal to 1, plus partial z partial y times dy by dx. And now we can find the various bits. The first thing is we know dz dx equals 0, because we know that z equals 0, and it doesn't matter when you differentiate 0, it doesn't matter what your variable is, you're still going to get 0. Partial z partial x, so that's this thing, with regards to x being the only variable, so that's going to give us a y, plus partial z partial y, so this thing differentiated with regards to y, which is going to give us x plus cos y, times dy by dx. And from there, it's just a very straightforward matter of rearranging that to get dy by dx by itself. So dy by dx equals negative y over x plus cos y. Okay, so we started off with a function in x and y, and we've managed to find out what the derivative of the function dy by dx is. So if we drew a graph of this, that's what the slope of it would be.